Hello, everyone. Welcome to the 2022 ACON seminar series. It's 3:30 here in Colorado, and it's an honor and a pleasure for me to introduce Dr. Gabriel Isaacman-VanWertz. Gabriel is an assistant professor in the Department of Civil and Environmental Engineering at Virginia Tech. He completed his PhD at the University of California, Berkeley, after which he spent 2 years as an NSF postdoctoral fellow at MIT. He's originally from the East Coast, growing up in Maryland and completing his undergraduate at Wesleyan University in Connecticut. His research focuses on understanding the chemical transformations or reactive organic compounds in the atmosphere. And today he's going to tell us about the competition between deposition and oxidation in the fate of atmospheric organics. I want to remind you that you can enter at any time questions in the window below the video you're seeing if you're watching on streaming, and I will read the questions at the end of the seminar. With that, Gabriel, please take it away.
Thank you so much for that very nice introduction, and thank you all for inviting me here and having me here. As you said, I'm Gabriel. I'm at Virginia Tech. I'm very excited to present some of the work that we're doing. Of course, there's a lot of stuff that our group does, and so I unfortunately won't be able to highlight all of my students' work, but I'm very excited to talk about deposition and oxidation in this cutely named talk that I've got here. So just for a quick big picture of what my research group in general does, and we'll talk about some of the specific projects as we go through. Our group is really focused on trying to understand organics in the atmosphere, both gas and particle phase. And we do it through a lot of instrument development and then new analytical technique development to try to make sense of that data, and then a lot of field deployment and field research as well. So, and I'm going to be showing data from a few of these projects today, including this tower that's there in the lower right. Before I jump into everything, I want to take a second to actually thank everyone who actually does this work and supports this work. So I'm going to be talking about some specific projects that are supported by the NSF and Department of Energy, some of our collaborators in France and the University of Virginia, and of course, all of the students and postdocs that are in my research group shown here on the lower right, which is mostly up to date. And in particular, I'm going to be talking about work from these three individuals, Deb McGlynn and James Hurley, who are two graduating PhD students in my group, and Shenyang Bi, who's a postdoc that's been working with me for a couple of years. So in sort of a big picture overview here, I think most of you probably have some idea that reactive organic carbon is quite important in the atmosphere. And it can be important in a lot of different ways. The way we think about it can sort of depend on the questions that we want to ask, of course. But I really like this nice overview slide from Colette Heald and Jesse Kroll at MIT that sort of generally lays out what all of the pathways are that produce the atmospheric outputs and impacts that we tend to really care about. So sort of what gets emitted and what reacts and then what gets formed at the end. And what's really clear from this really lovely diagram is that reactive organic carbon is a really large part of it, sort of no matter how you slice it. It's a big chunk of what gets emitted, it's a big chunk of what's doing the reacting, and it's a big chunk of the products in the atmosphere that we care about, particulate matter, ozone, CO2. Well, one of the really interesting things about reactive carbon, when you look at it in this sort of lens, is that in contrast to everything else kind of at that middle row, the stuff that we're emitting, reactive organic carbon is sort of a category as opposed to a compound, right? So if we look at all of these other things, SO2 or dimethyl sulfide or NOx, we're really talking about one, maybe two specific compounds. And when we're talking about reactive organic carbon, we're talking about some number of compounds. And one of the big issues, I think, is that we don't actually necessarily have a handle on that. And obviously knowing the exact number is not necessarily all that important, but one of the big issues that we face as people interested in organics in the atmosphere is that how we deal with how many are out there and what do we actually do with the fact that we don't know what they are, and how do we characterize them and categorize them is a really big question. And so that's one of the things that I'm going to be talking about today, or really the core of what I'm talking about today, which is to try to answer a couple of big picture questions. So first of all, how chemically diverse is the atmosphere, right? And we have some answers to that, and there really is no particularly satisfying answer to that. But going to try to ask that. To what extent does the fate or the impact of the carbon that's in the atmosphere really depend on the detailed chemistry that's there, right? If it's chemically diverse, but they all do the same thing, it's not that important. So to what extent does the chemical detail and the chemical structure really matter? And as a spoiler, we think it does matter. So how do we actually manage a system that's extremely complex and extremely chemically diverse? So we're going to answer the first two questions, or I guess I shouldn't say answer. So I'm going to talk about the first two questions really in the context of two specific projects that my group is working on. And we're going to put some bounds on how chemically diverse certain aspects of the atmosphere are, and to what extent detailed chemistry within that context is critical. So the category that I'm going to talk about first is biogenic emissions. So it's sort of what we can think of as kind of the natural aspects of reactive organic carbon. And so I have up in the upper right there, sort of the categories as laid out by Colette and Jesse. And so here we're really talking about sort of plants and other natural sources. And the way that our group studies that is through field deployment of instrumentation at a tower that's very close to University of Virginia. So this is a partnership between Virginia Tech, my group, and University of Virginia, which is led by Sally Pusady there, and a number of ecologists. And one of the really neat things about this site is that we have all sorts of atmospheric measurements, which I'll talk some about, but also all sorts of ecological measurements. So we can try to understand some of the drivers of this. So this tower, which we call the Pace Tower, because it's on the Pace Estate or the Virginia Forest Lab, is a 40-meter walk-up tower. The canopy height is maybe 20 to 25 meters. At the top of the tower, we have all sorts of fluxes of ozone, fluxes of NO and NO2. We have some NOI measurements. We have eddy covariance measurements. We have photosynthesis measurements. There's leaf temperature. There's all sorts of other stuff. But what my group is really responsible for is let's label there the BVOC, so biogenic volatile organic compounds. And basically the way we measure those is that roughly in the middle of the canopy, we're in somewhere around 20 meters. We have an inlet, it's a heated inlet, and we pull air down through that inlet to a autonomous, essentially sort of constantly running GCFID. So it's a gas chromatograph. So we take all of the gases that we're sampling, we concentrate them on a trap, and then we heat up the trap to get them off, and we separate them out on a chromatography column, and then we look at what comes out by flame ionization detection, which is essentially burning it and see how much burning there is. That's the main kind of backbone of our instrumentation. We also occasionally deploy a GCMS, gas chromatograph mass spectrometer, to measure some of the lower volatility stuff. I'm not going to talk too much about that. It's notable because the main way we do that is actually to sort of hand winch our sort of field deployable GCMS up to 20 meters and stick it in a box. So we have a little bit of data from that. I'm not going to talk about it too much, but we've been running this for about 2 years. And so in those 2 years, we've gotten quite a lot of data, and we've really focused on the biogenic emissions and the biogenic concentrations or the concentrations of biogenic compounds. And sort of a sample of what that data looks like. We sample about hourly. There's obviously some downtime because it's a field instrument. So this was the first year. We actually now have 2 years of this. And you can sort of see the seasonality in some of the major compounds like isoprene. You can see the rise in the summer from monoterpenes, which is 2 isoprene units. And we get a little bit of sesquiterpenes as well, which is 3 isoprene units. And because we have a GCMS and a GCFID, we can separate these compound classes into all of their individual components. We can kind of lay out what the system really looks like. And so monoterpenes, we can break down into the maybe dozen-ish major components of monoterpenes. And sesquiterpenes, we see something sort of similar, maybe 2 dozen of those. And so we get some really detailed understanding of it. But between this and a couple of other, or sort of the other compounds that we can see there and other research that's been done by all sorts of people before me, we can put some bounds on how many compounds we really think are in the atmosphere because of biogenic emission. And we can estimate that it's tens, maybe hundreds of different compounds from primarily a handful of chemical classes. So we can start to put some bounds on the initial diversity, at least of the emissions. But one of the things that we can actually do, because we have this separation of individual compounds, is we can start to ask, how much does it matter what the detailed differences between these chemicals are. And so one of the ways we can do that is we can say, okay, well, this is the concentration. It's roughly half one thing, alpha pinene to be specific. And then the next major one is beta pinene. You can see there's just a little shift in the double bond and so on and so forth. But what we see with this, and perhaps unsurprisingly, is that if we start to actually think about it in terms of atmospheric impacts, we see that some of the components, some of the minor components start to become more important. So for instance, for OH reactivity, some things react faster with OH than others, and they start to become more important. And this becomes particularly important for things like ozone reactivity. So once we scale this to reactions with ozone, this minor component, limonene, which is maybe 10% of the mixture, becomes like half of the ozone reactions. So we have this small change in structure becomes extremely important, right? So we get this idea that emissions maybe are moderately diverse, but differences in that diversity is relevant. And it's not just the impacts, right? It's also that they do not necessarily behave the same, even though they may be sort of what you might think of as the same class. So as an example, the monoterpene diurnal cycle looks something like this at the tower. We have a nighttime high, we have a daytime low. This sort of pattern is actually quite typical or what we think of as the monoterpene pattern. And we can see that the major isomer like alpha pinene basically follows this pattern. It's high at night, it's low in the day. That's true in the summer, it's true in the winter. And it kind of goes along being high and low and high and low. In contrast, this really reactive limonene behaves totally differently. In the winter and in the spring and in the fall, it more or less follows what alpha pinene does. But in the summer, it actually has a daytime high, right? So even though it's sort of a minor component, it's a major source of reactivity and it behaves differently, right? And you don't see that in the concentration necessarily, but we can take that concentration and we can try to split it apart into basically we use factor analysis to split it into monoterpenes that behave like alpha pinene and monoterpenes that behave more like that daytime high that we see in limonene. And the dominant factor of that is that nighttime high, daytime low, nighttime high that we just keep expecting. But there's this minor component of this daytime high, and that becomes extremely important in ozone reactivity. And so we're starting to see then that although the diversity is already somewhat daunting, it's actually that certain minor components or certain specific features of the components can be really important. And so we see that in natural systems. And it turns out we also see basically the same story if we look at other systems. So another project that we've looked at is what's in a fragrance. So this would sort of fall under other anthropogenic sources. You're probably all sort of familiar with the work that came out over the last several years that showed that consumer products and personal care products and things like that have become a major source of VOCs and chemical reactivity in urban environments. And so we actually worked with Brian McDonald and a few others to sort of ask the question of within these categories, what exactly are fragrances? So it actually, fragrance is essentially an industry term that often emissions databases just sort of say fragrance or provide a little bit of information. And so we wanted to know what those actually were. So we went in and we characterized about a dozen fragrances in a lot of detail. And we see something relatively similar. We can sort of characterize most of what we see into a handful of sort of category or compound classes. So we see things like terpenes, again, those monoterpenes. We see terpenoids, sort of linalool and related things, natural and synthetic fragrances, a handful of plasticizers. And we get this sort of similar idea that we had with biogenic sources, which is, we see tens to hundreds of compounds, mostly from a handful of chemical classes. So there's some diversity. It's not completely unmanageable. But if we go again and take these fragrances and say, well, let's imagine that we spray them onto a person and then we let that evaporate, right? That's what's going to happen to these. They're going to go into perfumes and get sprayed around and then evaporate. And let's model the evaporation. What's actually going to happen? And if we look at what's in that perfume, what the liquid contains, right? It looks like that slide that I showed before. But if we model what's actually going to evaporate, we again see dominance of a small subset of compounds or a small subset of compound classes. So the diversity is not totally overwhelming at this stage. But even within that diversity, we see that there's specific aspects or compounds or classes that we might be particularly need to be attuned to or that are particularly important. So if we go back and look at this question again, we can actually start to answer the first question, which is sort of how diverse is this actually? And we can put some numbers on this, right? I just said roughly there's maybe hundreds of compounds coming from biogenic sources and consumer products. Thanks to other work we've done, other work others have done, we can estimate the fossil fuels probably on the order of thousands of compounds. Again, mostly from a handful of sort of hydrocarbon chemical classes. And things get even a little dicier, but sure, we can put some numbers here as maybe roughly thousands of biomass burning compounds. Again, from some dominant compound classes, but that one I think we're still sort of trying to pin down. But whatever the case, we can sort of guess that the diversity of the atmosphere is hundreds to thousands of compounds. So that's already a fair amount. It's not nothing, right? It's maybe within the realm of possible to start to really speciate and handle. The problem, of course, is each one of those compounds, we take that compound and we put it in the atmosphere, and you have this cascade of reactions. And you're not meant here to actually read every little bit of this, but it's an example of alpha pinene there circled in red. And once you start actually reacting it in the atmosphere, you end up with all sorts of compounds. So there's modeling of this, of course, and there's measurements of this. If we go measure it, you see hundreds and models, sort of algorithmic models like the Gecko-A model that Bernard Armand and collaborators have built, and I'll talk a little more about later, estimate that basically for each compound you start oxidizing in the atmosphere, you generate, on the order of 10,000 compounds. Not all of them are going to be major, but still. So if we go back to this picture, then, we have hundreds or maybe thousands of things that we're emitting, and we're basically probably forming on the order of hundreds of thousands. And what we know about those hundreds of thousands from all of our work in the forest and from our work with fragrances is that maybe specific ones of those are more important, right? Those are the ones that will be reactive, or those are the ones that are going to have the outcome that we care about, right? And so how do we then characterize or categorize or deal with the fact that there's hundreds of thousands of compounds out there? How do we reduce that complexity? It's the issue that, people have been dealing with for probably decades. Definitely still was something being discussed when I started, and I think it's still something that we're all trying to sort out. So I'm going to basically spend the rest of the talk today trying to kind of lay out the framework of how we have been thinking about how we can manage a complex system like this, a molecularly complex system. And the way that I think about it, and the way that our group has started to really dive into this, is through what we call the sort of fate-based framework for atmospheric impacts or for a reactive organic carbon. And the concept behind this is basically sprang out of work that I was doing during my postdoc at MIT. And the idea is that if we have emissions of some compound, for instance here, alpha pinene, the first thing that it's going to do, in the atmosphere is react. So it's going to react and it's going to form a couple of products. Some of those products are going to be almost immediately particle phase, and some of those products are going to be almost immediately things like long-lived gases. But some fraction of the first thing it's going to form are these sort of lightly oxygenated compounds that may go on to form more particulate, may go on to form more long-lived gases, things like that. And so pretty quickly, we form this complex mixture of semi-volatile, lightly oxygenated, partly condensable gases. And pretty quickly in the atmosphere, those are just going to react again, right? If they are still reactive, they will continue to react. And so at a certain point, you're going to sequester basically any potential reactivity into things that aren't very reactive, right? You'll form all the particles you're going to form. You form all the long-lived gases you're going to form for the most part. And you're sort of stuck there in terms of atmospheric impacts. And somewhere along this line, you're going to remove carbon from the atmosphere, right? Carbon doesn't stay in the atmosphere forever. It has to get deposited to the Earth's surface. And so then the impact of a gas that we release, or an impact of a gas that's in the atmosphere, is essentially a function of can deposition outcompete oxidation, which is to say, does it deposit before those initial steps of oxidation can happen, or is it allowed to get to its endpoint? Because if it's allowed to get to its endpoint, it gets to its endpoint. Now, where it gets deposited, of course, can also be important, and other interesting things can happen, right? Some of the things I'm showing there have, can photolize, and so it's not a complete endpoint in chemistry. But fundamentally, I think in trying to understand some of the big picture outcomes here, one of the big questions is, does deposition outcompete oxidation? And one of the big issues that we have is that we have a decent handle on the oxidation side of that. In this particular system, so alpha pinene oxidation, what we showed in 2018 or so, in experiments we did in 2016, 2015, was that we pretty much reached this sort of oxidative endpoint within a few hours, right? And within a few hours is sort of on the scale of hours, or sorry, it's on the scale of, maybe tens of kilometers or a bit farther. But we really didn't have at that time a good handle on what the time scale for deposition was. Right. So a lot of what we're now trying to understand is, what is that time scale for deposition, and can it compete, on that scale of hours that we're seeing as the time scale for oxidation. Now, of course, that time scale for oxidation is a function of what compound it is, what's your environment, all these other questions. But in most cases, we think that we can more or less estimate that it's probably on the order of hours. 3 hours is probably overly specific. So the question then is, what is the timescale for deposition? Is it competitive with that or not? And it's not a particularly easy question to answer, but we do have some data that is helpful for that. We also have some models that are helpful for that, and many of the people in this virtual room have been involved with that, and I would be very happy to talk with them more about it. But roughly speaking, the deposition velocity, so the speed with which something travels to the Earth's surface, has been broadly shown to be a function of Henry's law. So that's approximately gas solubility, although that's a little bit imprecise. And so the deposition velocity of particles is probably on the order of tenths of a centimeter per second. And what Tran Nguyen showed in the southeastern US as part of SOAS, and what others have shown in other environments, is that the deposition velocity of gases is maybe 1 to 10 centimeters per second, and that it roughly goes as a function of Henry's law. And so if we make some pretty basic assumptions about that atmosphere, we say that we've got a well-mixed boundary layer, we put some constraints on that boundary layer, we can basically just calculate, given these measured deposition velocities, what the time scale for a gas to get to the surface is. And we see that that's pretty much a function of Henry's law, and that eventually it kind of flattens out as Henry's law and uptake at the surface no longer becomes some of the limiting factor. And if we say, well, at this low end, maybe there's other things going on, we can actually put kind of an empirical constraint then on how fast we'll lose something, or what the deposition lifetime is as a function of Henry's law. So if we do that, then we can take this bigger picture framework of fates and start to apply it to individual molecules. We can say, okay, well, a molecule can either oxidize in the gas phase, or it can deposit in the gas phase, or it can go condense into a particle. And if it's a particle, it can deposit as a particle, it could come back out, or it can go on and oxidize in the particle. And I'm, to be honest, not really going to talk too much about oxidation in the particle, in part because we don't have great timescales for that yet. And in part because if it oxidizes in the particle but stays within the particle, then it sort of still just deposits as a particle, although there will obviously be some transformations. So we can discuss then the impact on regional atmospheric chemistry, on formation of particles, things like that, as basically this competition between the oxidation process, that purple arrow, and the deposition process, and particularly deposition of the gas, or before it forms particles, if that's what we're concerned about, or deposition in either phase. So we can take that sort of empirical fit that I showed before and take all the data off it so that it looks nice and pretty like this. And we can look at the deposition timescale as a function of Henry's law. So now it's sort of flipped the other way, so that we have more soluble things on the left and less soluble things on the right. And what you see is for really soluble gases, you sort of cap out at a certain deposition lifetime, basically velocity toward the surface, and less soluble things go a little bit slower. And for oxidized gases, at least for oxidation products, that we actually know that Henry's law constant is actually very closely correlated to vapor pressure. So Almahajic showed this in 2014, and we showed it sort of empirically for a whole bunch of products, oxidation products of several hydrocarbon precursors in 2021. And what that means is that we can actually then use Henry's law constant as sort of a proxy axis for vapor pressure as well. Right. And for vapor pressure, then we can actually then start to estimate whether things are going to be in the particle phase or in the gas phase. Right. So we can, for sort of typical atmospheric conditions, so to speak, we can basically plot the fraction that you expect in the particle phase as a function of its vapor pressure. And we can line that vapor pressure up with Henry's law. And it's not perfect, right? There's non-ideality, and we have to make assumptions about the organic loadings in the atmosphere and things like that. But what we can estimate then is if particle deposition happens maybe on the time scale of roughly a week, right? If particle deposition is in large part a function of how frequently does it rain, and maybe it roughly rains globally on time scales of a week. And this is assumptions that we're trying to clean up a little bit. We can nevertheless kind of make this broader statement that generally gases, or the timescale for deposition is a function of gas solubility on the right, and then particle time deposition on the left, and there's a transition in between where you're sort of partitioning between the gas and the particle phase. And so we have a timescale for deposition that's a function of gas solubility, or Henry's law constant, and particle fraction, which is basically vapor pressure. And we can put this all on the same axis. We can do the same thing for oxidation. So we can say, well, the oxidation lifetime is just directly, correlated with the reaction rate, at least if we're talking about oxidation lifetime with a specific oxidant, right? So we can have deposition lifetime as sort of log linear with KOH, or sorry, oxidation lifetime. But again, we have this issue where that's only really true in the gas phase. As you get to things that are more and more in the particle phase, right, heterogeneous oxidation is probably fairly slow. Now, again, there are caveats here where there's in-particle oxidation, and there are probably conditions where oxidation, heterogeneous oxidation of particles is probably not completely negligible. But we have some decent ideas in most cases from some lab experiments that it takes quite a long time to oxidize particle phase through OH alone. And so we end up with this sort of gradient that says as you get more and more into the particle phase, your effective gas phase oxidation lifetime slows down, right? And so we can end up with sort of this two-dimensional space where, again, because Henry's law is correlated with vapor pressure, we can say that oxidation lifetime is sort of linear or log linear with KOH as you go up that y-axis. And then along the x-axis, you basically have a gas on the right and a particle on the left. And if we make some basic assumptions about how slow particle lifetime is, you can kind of feel out this transition in between. So it gives us this idea then that overall our time scale for oxidation looks something like this, right? And our time scale for deposition, which in sort of two-dimensional space looked like that, we can put on the same axis, right? Time scale for deposition has basically no impact on or no effect from KOH or from reaction rate. And instead, you just get this sort of smooth metric all the way across. And so it means that for any given compound, we can use its sort of physicochemical properties to actually understand what these various fates are, and maybe start to talk about the competition, right? And so we can actually then say, well, if something is going to react or not is a function of how quickly it deposits versus how quickly it oxidizes. And so we end up with this fate that's basically just the ratio of the reaction rates. So if we just literally put one on top of the other, you end up with a plot that looks something like this. And so you can see that in the lower left, we have things that react slowly and are quite soluble. And so they're going to deposit. And in the upper right, we have things that react quickly and do not have high Henry's law constants, which is to say they're not particularly soluble. Again, solubility being kind of a shorthand here. And so those are going to oxidize. right? So we can say, well, this is the ratio of these timescales, and we can reframe that as, which fate is actually going to win, right? So based only on a compound's KOH and Henry's law constant, we can start to say, okay, well, in the upper right, we've got a pretty strong oxidation fate. In the lower left, we've got a pretty strong deposition fate. And somewhere in between, we've got a little bit of a gray area. And we can go a little bit farther, and we can say, well, based on the correlation between Henry's law and vapor pressure, we can kind of estimate whether we have particle deposition or gas deposition versus oxidation. And so then you end up with this relatively narrow, what I sort of call transition region, where the fate's not so clear, where within these sort of darker bounds, you're at sort of 25%, 75%, and within the broader bounds, you're sort of 10%, 90%, right? And so in there, then the fate is somewhat competitive. And everywhere else, we can more or less assume it's just going to go down its pathway, right? It's either going to deposit or it's going to oxidize. Again, sort of broadly speaking. So the question then for us is where is the atmosphere, right? Where does this actually all fall out if we actually want to try to characterize those hundreds of thousands of compounds? So to do that, for starters at least, I needed a data set of thousands or tens of thousands of compounds that I could put in terms of their physicochemical properties, right? And so in order to do that, I turned to Bernard Aumont and the Gecko-A model, which takes hydrocarbon precursors of whatever type, uses the basic chemical reactions we know happen in the atmosphere, and sort of predicts the multiple generations of oxidation that are going to happen afterwards. And it'll go kind of infinitely, so you have to make some cutoffs and make some decisions about which compounds you're actually going to include. But in any case, I used sort of three precursors and estimated roughly 40,000 products that would be formed out of those three precursors. And the neat thing for these is that we have specific structures, right? This is sort of a chemical oxidation pathway. And so we know the exact structures for each of these. And so then we can go and actually use all of our various structure activity relationships to actually estimate their physicochemical properties, right? We can take these 40,000 compounds and we can put them in terms of their KOH and the Henry's law and all of that. So we did that. One of the really sort of fun side effects of this is that we could start to ask the question, how different are two different molecules in their vapor pressures and their Henry's law, et cetera. And we could really start to ask, how much does structure matter within that, right? Do two isomers differ by a lot or a little? How much do we really need to care about the details of the chemistry? So take a quick foray into that. What we found was that generally speaking, two isomers differed by roughly 1 order of magnitude in their vapor pressure. So this is sort of a histogram of differences in vapor pressure between isomers. And we can do this for all of our various different estimation techniques. And we see that that's roughly sort of comparable between all of them. We can also say, well, we have all these vapor pressure techniques. How different are they? Because that gives us some idea of the uncertainty. And we find that the difference in the estimation of any two vapor pressure techniques is lower than that. So the disagreement between methods is sort of lower than the difference in vapor pressures. So we start to get this idea that there are real differences between the vapor pressures of different isomers, which again gets at this idea that individual components within our mixtures could sort of play outsized roles. We see the same thing for Henry's law. We see the same thing for KOH, that the difference in Henry's law between two compounds is roughly 2 log units, or two isomers is roughly 2 log units, factor of 2 for KOH. So even small tweaks in the structure can have relatively important impacts. But of course, the question we really want to know is given that fact, where do these all fall within our kind of fate square that tells us what's actually going to happen? And so we can populate that square with all 38,000 products that we made. And we see that by and large, they're actually going to tend to prefer to deposit, but that a huge fraction of them are kind of in what we might call that transition regime, right? A lot of the atmosphere is in that sort of uncertain or unknown transition window. And again, remember that Henry's law is uncertain to 2 orders of magnitude, and vapor pressure to 1, and KOH to a factor of 2. So So exactly where that white line falls is definitely a little bit debatable. We can also answer some interesting questions about what level of detail we actually need to care about. So in some cases, for instance, we can look at a couple of compounds that have the same formula, but fairly radically different fates, right? Depending on the exact structure, some compounds might be more in the transition versus more sort of solidly depositing. In other cases, that's less true, where there's a lot of different possible structures, but they all kind of fall in some of the sort of same general region. So one of the interesting things we can say about this then is for one thing, it starts to give us some hint into where we actually need to focus our understanding, right? If you look at this mixture here, uncertainty in Henry's law actually doesn't matter that much. If Henry's law were, 2 orders of magnitude higher or 2 orders of magnitude lower, we would still be in more or less the same sort of rough fate, right? Whereas in other cases, that might not be the case, right? And we can actually start to ask some big picture questions about the atmosphere as well, right? So the average KOH of your sort of typical oxidation product, which we know thanks to our 38,000 compounds, is roughly here. So what we see then is that it's competitive between oxidation and deposition. So it's very much in the region that we need to have a good understanding of. We also see that we're actually fairly insensitive to differences in Henry's law once you're past a certain point, right? So by this estimation, roughly 10 to the 5 or so, if your KOH or if your Henry's law is higher than that, it probably doesn't really matter. And one of the really interesting things about that is that Chris Knode and Alma Hodgick and Jose Jimenez, at least a few of whom I think are on this call, used a global model to kind of come to a very similar conclusion maybe 6-7 years ago, that beyond a certain point, and that point is not so far off of here, that Henry's law probably is not any more a controlling factor. We can also then sort of plot it more directly as the competition between these fates, right? We can ask, if we have a deposition lifetime versus an oxidation lifetime, in the middle it's competitive, and on either side, we have one fate preferred over another. And so we can see for certain compounds, you can see how there's slight differences in these in kind of the outcomes that you might expect for a given structure, right? So the one compound here is very likely to oxidize because it has that available double bond, whereas the others are not. And that's sort of varies widely across all of these compounds. So some might be sort of a handful of compounds, but with very different fates. Some might be a lot of compounds with a range of fates, and some might be, different isomers all have the same fate. So we can start to ask then again, for those 38,000 compounds, what fraction are actually in regions that we really need to be kind of, I wouldn't say concerned about, but thinking about. And so we can plot the whole suite again in kind of this space. And again, we see that by and large, compounds are likely to deposit, but now they're actually sized by how high they are in relative concentration in the model. And we see that there's quite a bit of spread. And if we actually kind of highlight that 3-to-1 region here, that the sort of a large fraction, something actually like half of all of the carbon is in this region that we still have to kind of pin down. So the sort of key point here then is we can start to use these really fundamental physicochemical properties to understand the fates and hone in on which compounds we actually maybe need to be thinking hardest about and which properties we need to be thinking hardest about. But that maybe unfortunate upside is that, or upshot is that quite a lot of the atmosphere appears to be in these pockets of particularly subtle or important sort of competition. What we're trying to do now is refine this whole approach somewhat. We're trying to get a bit more precise and understand how it actually can vary sort of across the globe and across the region. So the first thing that we've been trying to do is understand kind of the sensitivity of the gas deposition. So we've been using a sort of a resistance model that's shown on the left to actually a little bit more closely try to recreate some of the data that we based that original empirical fit on. We are using here basically the parameters that she originally used in calculating some of those values. So It's not really a huge surprise that the model fits these data, but now that we sort of have a decent way to look at this, we can actually start to question what the sensitivity is. How sensitive is it to boundary layer height and leaf area index and resistance and things like that. But the other big thing that we're really trying to do, and I'd love to talk with anyone about, is trying to move from only dry deposition to actually thinking about wet deposition as well. And so the place that we've really started trying to look at that is to use basically global measurements from the Department of Energy ARM sites, the atmospheric radiation monitoring sites, where they measure in a lot of detail with high time resolution precipitation. And so we can really look at what the precipitation size distributions are and weight rates are and all sorts of this all across the globe. And so on the right, we're showing 4 sites that we've sort of selected as being different and dispersed around the globe. And on the left, the precipitation histograms, basically frequency distributions. So in Manaus in Brazil, it rains basically 16% of the time. And in central US, it rains like 10% of the time. That Norway value, that one in red, I have some questions around. Actually, we think that might be snow based on the timing. So this is very new, and we're still very much trying to suss out all of the issues here. So take this last little bit with some grains of salt. But we can use these data to kind of start to place global distributions and global constraints on what the wet deposition timescales would be. And the first thing that we actually see is that if we just look at the rain properties, we find that in an average by hour, I should say, we've currently started by kind of looking this from an hourly average perspective. We find that within a rain event at all of these sites, the most soluble gases basically get washed out within an hour or two. So that within a rain event, we basically lose the soluble gases and there's some tail off on the less soluble things. Again, you see kind of a range that roughly kicks in around 10 to the 5th in Henry's law, which is what we saw for dry deposition as well. If we ask the broader question though of what about, not just in a rainstorm, but we account for the frequency of rain, then we can actually look at sort of the overall time scale. And we do this by basically randomly sampling hours and seeing how long it takes of randomly sampling hours to actually deplete our compounds. So it's sort of a Monte Carlo style approach. And we see that on the order of 10 hours is enough to deplete most soluble gases, even at most of these sites. Again, I have some questions about Norway. And we find that the timescale for wet deposition is roughly equivalent to just what is the timescale for rain frequency, right? So if it rains out, if within an hour of rain, most compounds are gone, well, in Cordoba, it rains, every 5 hours or so on average, et cetera. And so we find that the timescale here is roughly 10 hours for soluble gases and then downward. Or I should say upward. And we can look at how this compares to dry deposition, and it's sort of like right in that range. And so we find that wet and dry deposition are roughly competitive, but it depends, of course, on rain frequency, and probably depends on boundary layer height, on surface properties. And so we're really trying to understand how sensitive everything is to all of that. And lastly, then try to understand what the actual global distribution of this competition looks like, and then what the global distribution of the competition between oxidation and deposition looks like. So with that kind of last project, that's really where we're going now. And so we're really sort of just getting started and welcome thoughts and collaborations on that. I'll just leave you with these thoughts with the sort of radical 90s background, which is not entirely meaningless. That is the sort of fate square in the background, but I enjoy how very 90s it makes my slides look. Just a couple of thoughts that it's pretty clear the atmosphere is really chemically diverse, and that every molecule behaves differently, both sort of temporally and also chemically. And that's not necessarily an easy problem to solve. And that the differences, very small differences in structure, can really meaningfully impact all the physicochemical properties of a molecule. And so we can use, we're trying to get to a place where we're really trying to use not necessarily the structure or I don't want to say artificial, but I guess I'll say artificial shoehorned categories, based on structure or formula or whatever, and instead of really try to categorize our molecules based on what their actual likely impact on the atmosphere is. But it's made difficult by the fact that really an enormous amount of the reactivity that we see and the carbon that we see is in these regions that are somewhat uncertain to certain or at least quite competitive. And so with that, I think I have time for questions. I think I'm right on time.
Yeah, you're remarkably on time. Well done.
I was impressed.
The super interesting presentation. It's quite a lot to think about. Let's see if we get some questions from Slido. We're getting a question from the Zoom crowd. Very good. Christopher Lawrence is asking, any plans to include aqueous oxidation in this methodology? Many compounds have much quicker reaction rates with OH in the aqueous phase compared to the gas phase, potentially making the system a lot more sensitive to differences in Henry's law.
Yeah, it's a great question. I'm sure it did not escape you that I pretty much upfront sort of said I wasn't going to be treating in particle oxidation at the moment. I would like to. I have thought a bit about how to do that, and the truth is I don't have great ideas yet, and I'm open to those ideas. There's a couple of sort of logistical barriers to it. I mean, one of them off the bat is just the number of dimensions in any really intuitive space. But the other being that I guess I'm not totally aware of a lot of structure activity relationships to predict those. So it gets hard to sort of implement on a large scale. I mean, I guess some of them actually do have OH rates. Yeah, it might be doable. I guess OH in the aqueous phase does have structure activity relationships, I think. And so that might be possible. I have thought some about it, and I need to think more about it because I agree that I do think it needs to be like in particle oxidation is sort of blatantly missing from this formulation. Some of that is because there's a lot of uncertainty. Some of that is because of these logistical issues. And some of that is because I'm still struggling a little bit to figure out how best to think about that and implement it, to be honest.
Okay. Emily Franklin say, great talk. Can you comment on how to include all the compounds that we measure but cannot determine the structure of?
Yeah, I mean, that's a great question. It depends on how you measure it, right? I guess is part of the answer. Like if the measurement is inherently structureless, which is to say, if it's something like a direct mass spectrometer, I think that some of the unfortunate upshot of the talk is that I don't think you can, because of the sort of clear differences. Like we now know that isomers differ sort of statistically significantly in their vapor pressures, in their Henry's law, and their KOH. And so without some structural information, then you have a bit of an issue in that context. That said, there's a lot of interesting things you can do with our measurements that can try to get at that. You know, if you've got a GC measurement, there are ways to get things like vapor pressure out of their retention time, things like that, right? There might be ways that we can try to get at KOH out of fragmentation by trying to pick out pieces of double bonds and things like that. So I think that in the end, you do need something, because you've sort of shown that isomers can vary in their fates. And so you need some structural fragment to hang on to. But it's a problem, certainly. Yeah, I mean, I think that's one of the places we need to go, is trying to figure out how to get all of this information all at the same time.
So while we wait for more questions, I have probably a very naive question, but I was expecting at some point you mentioning the morphology of the terrain somewhere.
Yeah, so
because especially for biogenic stuff emitted from a forest, is going to be like what's going to be the total surface that the gas is going to see, or is that negligible compared to other
so
factors?
the really amazing thing about the ARM database is that it's not actually a precipitation rate database, although that's there. It's actually a precipitation size distribution database, amongst other things. I mean, not at every site, but the 4 sites that I showed, we are actually using precipitation size distributions. So it is, I guess, it's in morphology in that sense, which is to say that we are not using some presumed droplet size and some precipitation rate. We're very specifically using the actual data of like this many small droplets, this many big droplets, etc. So one of the things that is so far interesting, although we have some admitted doubts about some of our math and we're working on it, is that it kind of seems like either rain is sufficiently average that it doesn't seem to be playing a huge role, or that it's sufficiently variable that it washes out. It's not clear. What we do see, right, and I sort of showed this as everything kind of collapses within a rainstorm, right? What it seems to be the difference between sites is frequency of rain. But all of the rainstorms don't quite look the same. So we're actually not 100% sure why that is, which is why we're a little bit skeptical. But it seems like at least droplet size distribution is not as important as we expected. I don't know if there's other morphologies you were thinking about.
Yeah, no, I was thinking also, the difference between, a conifer forest versus I don't know, something else that has less surface for dry deposition.
Oh yeah. So for dry deposition, so right now for dry deposition, we are using the parameters that Tran used for the southeastern US, which has in it certain assumptions. So things like leaf area index they are built in there currently. We have broken them out in our implementation so that we can start to test that sensitivity. But yeah, that's very much what I would really like to do, is globally, incorporate leaf area index, boundary layer height, whatever we can about surface, and then rain frequency, which are all things that like a large model really has pretty readily available, and just see if those things alone, what the distributions look like that. So yes, we're talking about that for dry deposition. We haven't really gotten there yet.
Okay, so we have Jose asking, have you explored the uncertainties if we knew composition and functional groups, but not detailed geometry?
Yeah, I mean, that's a great question. The structure activity relationships largely are ignoring detailed geometry anyway. It's not totally true, right? There's a little bit of secondary effects, like, groups are next to other groups, but the drivers of most of the structure activity relationships that I'm using to build it out are functional group based anyway. I mean, in particular for things like KOH, I mean, you really primarily need to know if there's a double bond, right? If there's a CC double bond. So if you can get at that, that's huge. For some of the oxygenated things, right, there's really big differences between, OH and a carbonyl, but maybe not as much between OH and hydroperoxide group, right? Like things like hydrogen bonding. And again, that depends on the question you're asking. So yes, I mean, I think Jose, you're fundamentally on the nose, that I don't know that it's necessarily, I guess I use structure as a shorthand for that, but I don't necessarily know that it's structure or geometry so much as it's functionality is probably a better word.
Very good. And Mary Barth is asking, for your precipitation database, are you using entire year information, or have you focused on spring, summer, early fall, when biogenic VOCs are more abundant?
Yeah, it's a great question. The truth is we're sort of not even really asking that question yet. We are currently, not every site has full data coverage. So SGP, we're actually using the full 2 years. I'm sorry, not the full 2 years. There's years and years of it. We're using 2 full years. For some of the others, I should say, Shenyang is grabbing like 6-month chunks. And so we haven't quite gotten to, like, one of the reasons I don't think I trust Norway is because I'm pretty sure he grabbed a winter chunk, so that can't actually be rain. It's got to be snow, because it's like northern Norway. And so the short answer is, whatever we were grabbing at the moment. But this sort of gets at what I was getting at earlier is as we start to move forward and try to look at this at more a global level, really trying to sort of suss out the seasonality of some of it and things like that, because there's also differences in boundary layer. And as you change the boundary layer, the competition actually changes because the two deposition terms scale differently with boundary layer height slightly. So there's all sorts of other things going on. So the short answer for Mary is we're just sort of grabbing it at the moment, but we're working on trying to get a little bit more organized about it.
Very good. Okay, looks like we don't have any more questions on Slido. Maybe let's wait a few more seconds. And if that's the case, then I'll thank you once more for the great talk, and see you everybody next time in 2 weeks.
Thank you all for having me.